Now for the third topic for water pollution, which is all about water pollution in lakes. And there will be 8 subtopics for this topic. And these are stratification and turnover, biological zones, lake productivity, eutrophication, algal growth requirements, the limiting nutrient, control of phosphorus in lakes, and acidification of lakes. For the introduction of water pollution in lakes, a knowledge of lake systems is essential to an understanding of the role of phosphorus in lake pollution. The study of lakes is called limnology. This section is essentially a short course in limnology as it relates to phosphorus pollution. Now for the first subtopic of water pollution in lakes, which is about stratification and turnover. Nearly all lakes in the temperature climatic zone become stratified during the summer and overturn in the fall due to changes in the water temperature that result from the annual cycle of air temperature changes. In addition, lakes in cold climates undergo winter stratification and spring overturn as well. During summer, the surface water of lake is heated both indirectly by contact with warm air and directly by sunlight. Warm water, being less dense than cool water, remains near the surface until mixed downward by turbulence from wind, waves, boats, and other forces. Because this turbulence extends only a limited distance below the water surface, the result is an the layer of mixed warm water, the epilimnium, flowing on the lower water, the hypolimnium, which is poorly mixed and cool. Because of good mixing, the epilimnium will be aerobic. The hypolimnium will have a lower DO and may become anaerobic. The boundary is called thermocline because of the sharp temperature change that occurs within a relatively short distance. The thermocline may be defined as a change in temperature with depth that is greater than 18 C per m. You may have experienced the thermocline while swimming in small lake. As long as you are swimming horizontally, the water is warm, but as soon as you treat water or dive, the water turns cold. You have penetrated the thermocline. The depth of the equilibrium is related to the size of the lake. It is as little as 1 meter in a small lake and as much as 20 meters or more in large lakes. In the fall, as temperatures drop, the epilimnium cools until it is more dense than hypolimnium. The surface water then sinks, causing overturning. The water of the hypolimnium rises to the surface where it cools and again sinks. This lake thus become completely mixed. If the lake is an cold climate, during winter, this process stops when the temperature reaches 4 degrees Celsius. Since this is the temperature at which water is most dense, further cooling or freezing of the surface water results in winter stratification. For spring, as the water warms in the spring, it again overturns and becomes completely mixed. Thus, temperature climate lakes have at least one, if not two, cycles of stratification and turnover every year. So that's all for the stratification and turnover. Now, next is all about biological zones. There will be 3 subtopics for biological zones. And these are euphotic zone, littoral zone, and benthic zone. So, biological zones. Lakes contain several distinct zones of biological activity, largely determined by the availability of light and oxygen. The most important biological zones are the euphotic, littoral, and benthic zones. So first, euphotic zone. The upper layer of water through which sunlight can penetrate is called the euphotic zone. All plant growth occurs in this zone. In deep water, algae are the most important plants, while rooted plants grow in shallow water near the shore. The depth of the euphotic zone is determined by the amount of turbidity blocking sunlight penetration. In most lakes, the turbidity is due to algal growth, although color and suspended lakes may substantially reduce sunlight penetration in some lakes. In the euphotic zone, plants produce more oxygen by photosynthesis than they remove by respiration. Below the euphotic zone lies the fundal zone. The transition between two zones is called the light compensation level. The light compensation level corresponds roughly to a depth at which the light intensity is about 1% of unattenuated sunlight. Next is littoral zone. The shallow water near the shore in which rooted water plants can grow is called the littoral zone. The extent of the littoral zone depends on the slope of the lake bottom and the depth of the euphotic zone. The littoral zone cannot extend deeper than the euphotic zone. Third is benthic zone. The bottom sediments comprise the benthic zone. As organisms living in the overlying water die, they settle to the bottom where they are decomposed by organisms living in the benthic zone. Bacteria are always present. The presence of higher life forms such as worms, insects, and crustaceans depends on the availability of oxygen. So that's all for the second subtopic. For the third subtopic, which is about lake productivity, and we will be discussing four classification of lakes, and these are oligotrophic lakes, eutrophic lakes, mesotrophic lakes, senescent lakes. So for the introduction of lake productivity, the productivity of a lake is a measure of its ability to support a food web. Algae form from the base of this food web, supplying food for the higher organisms. A lake's productivity may be determined by the measuring the amount of algal growth that can be supported by the available nutrients. Although a more productive lake usually will have a higher fish population, the number of the most desirable fish may decline. In fact, increased productivity generally results in reduced water quality because of undesirable changes that occur as algal growth increases. Because of the important role productivity plays in determining water quality, it forms a basis for classifying lakes. So first is oligotrophic lakes. Oligotrophic lakes have a low level of productivity due to a severely limited supply of nutrients to support algal growth. As a result, the water is clear enough that the bottom can be seen at considerable depths. This, as a result, the water is, in this case, the euphotic zone often extends into hypolimnium, which is aerobic. Oligotrophic lakes therefore support cold water game fish. Lake Tahoe on the California-Nevada border is a classification which is example of an oligotrophic lake. So next is eutrophic lakes. Eutrophic lakes have a high productivity because of an abundant supply of algal nutrients. The algae cause the water to be highly turbid, so the euphotic zone may extend only partially into the hypolimnia. As the algae die, they settle to the lake bottom, where they are decomposed by benthic organisms. In a eutrophic lake, this composition is sufficient to deplete the hypolimnium oxygen during the summer stratification. Because the hypolimnium is anaerobic during the summer, eutrophic lakes support only warm water fish. In fact, more cold water fish are driven out of the lake before the hypolimnium become anaerobic because they generally require dissolved oxygen levels of at least 5 milligrams per liter. Highly eutrophic lakes may also have large mats of floating algae that typically impart unpleasant taste and odors to the water. So third is mesotrophic lakes. Lakes which are intermediate between oligotrophic and eutrophic are called mesotrophic. Although substantial depletion of oxygen may have occurred in the hypolimnium, it remains anaerobic. Fourth is senescent lakes. These are very old, shallow lakes which have thick organic sediments and rooted water plants in great abundance. These lakes will eventually become marshes. So that's all for the third subtopic, which is lake productivity. Let's go now for the fourth subtopic, which is about eutrophication. Eutrophication is a natural process in which lakes gradually become shallower and more productive through the introduction and cycling of nutrients. Thus, oligotrophic lakes gradually pass through the mesotrophic, eutrophic, and senescent stages eventually filling completely. The time for this process to occur depends on the original size of the lake and on the rate at which sediments and nutrients are introduced. In some lakes, the eutrophication process is so slow that thousands of years may pass with little change in water quality. Other lakes may have been eutrophic from the day they were formed, if nutrients level were high at that time. So for cultural eutrophication is caused when human activity speeds the process naturally occurring by increasing the rate at which sediments and nutrients are added to the lake. Thus, lake pollution can be seen as the intensification of a natural processes. This is not to say that eutrophic lakes are necessarily polluted, but that pollution contributes into the eutrophication. Water quality management in lakes is primarily concerned with slowing eutrophication to at least the natural rate. To understand the factors involved in eutrophication, it is necessary to understand the factors contributing to algal growth. So that's all for eutrophication. Now for the fifth subtopic, it is all about algal growth formants, and there are four things to be discussed, which includes carbon, nitrogen, phosphorus, and trace elements. All algae require macronutrients such as carbon, nitrogen, and phosphorus, and macronutrients such as trace elements. For algae to grow, all nutrients must be available. Lack of any one nutrient will limit the total algal population. The availability of each nutrient in each natural cycle are summarized below. First, carbon. Algae contain their carbon from carbon dioxide dissolved in the water. Because the carbon dioxide is in equilibrium with the bicarbonate buffer system. The immediately available carbon is determined by the alkalinity of the water. However, as carbon dioxide is removed from the water, it is replenished from the atmosphere. The atmosphere is, of course, virtually inexhaustible source of this gas. When algae are either consumed by higher organisms or die and decomposed, the organic carbon is oxidized back to carbon dioxide, which returns either to the water or to the atmosphere to complete the carbon cycle. Nitrogen cycle. Nitrogen cycles from nitrate to organic nitrogen to ammonia and back to nitrate as long as the water remains aerobic. However, in aerobic sediments and in the hypolimnion of eutrophic lakes, when algal decomposition has depleted the oxygen supply, nitrate is reduced by anaerobic bacteria to nitrogen gas and lost from the system in a process called denitrification. Denitrification, denitrification reduces the average time nitrogen remains in the lake system. Denitrification, some of photosynthetic microorganisms can also fix nitrogen gas from the atmosphere by converting it to organic nitrogen. For phosphorus. Phosphorus in lakes originates from external sources and is taken up by the algae in the inorganic form and incorporated into organic compounds. During algal decomposition, phosphorus is returned to the organic form. The release of phosphorus from dead algal cells is so rapid that only a little of it leaves the epithelium with the settling algal cells. However, little by little, phosphorus is transferred to the sediments, some of it undecomposed organic matter, some of it precipitates of iron, aluminum, and calcium, and some bound to clay particles. Trace elements. The quantities of trace elements is required to support algal growth are so small that most fresh waters have sufficient amounts for a substantial algal population. So that's all for this subtopic. Now, for the sixth subtopic is all about the limiting nutrient. In 1840, Justin Liebig formulated the idea that growth of plant is dependent on the amount of foodstuff that is presented to it in minimum quantity. This is now known as the Liebig laws of the minimum. As applied to algae, it means that algal growth will be limited by the nutrient that is least available. Of all the nutrients, only phosphorus is not readily available from the atmosphere or the natural water supply. For this reason, phosphorus is deemed the limiting nutrient in lakes. The amount of phosphorus controls the quantity of algal growth and therefore the productivity of lakes. So for the relationship between summer levels of chlorophyll A and measured total phosphorus concentration for 143 lakes. Chlorophyll A, one of the green pigments involved in photosynthesis, is found in all algae. So it is used to distinguish the amount of algae in the water from other organic solids such as bacteria. It has been estimated that the phosphorus concentration should be below 0.010 to 0.015 milligrams per liter to limit algae blooms. So that's all for this subtopic. Now for the next subtopic, it's about control of phosphorus in lakes. There are three things to be discussed here, and these includes municipal and industrial wastewaters, septic tank sewage, agricultural runoff. So control of phosphorus in lakes. Because phosphorus is usually the limiting nutrient, control of cultural eutrophication must be accomplished by reducing the input of phosphorus to the lake. Once the input is reduced, the phosphorus concentration will gradually fall as phosphorus is buried in the sediment or flushed from the lake. In conjunction with reduced phosphorus inputs, these measures can help speed up the removal of phosphorus already in the lake system. Of course, the need to speed the recovery process must be weighed against the potential damage from inundating shoreline areas with sludge and stirring of toxic compounds buried in the sediment. To be able to reduce phosphorus inputs, it is necessary to know the sources of phosphorus and the potential factors for their reduction. The natural source of phosphorus is in the weathering of rock. It is exceedingly difficult to reduce the natural inputs of phosphorus. If these sources are large, the lake is generally naturally eutrophic. For many lakes, the principal sources of phosphorus are the result of human activity. Most important sources: 1. Municipal and industrial wastewaters. 2. Seepage from septic tanks. 3. Agricultural runoff carries phosphorus fertilizers into the water. So, for the municipal and industrial wastewaters, all municipal sewage contains phosphorus from human excrement. Many industrial wastes are high in this nutrient. Municipal wastewaters also contain large quantities of phosphorus from detergents containing polyphosphate, which is a chain of phosphate ions linked together. Next is septic tank seepage. The shore of many lakes are dotted with homes and summer cottages, each with its own septic tank and the tile filled for waste disposal. However, with time, the capacity of the soil to absorb phosphorus is exceeded and any additional phosphorus will pass on into the lake, contributing to eutrophication. The time it takes for phosphorus to break through to the lake depends on the type of soil, the distance to the lake, the amount of wastewater generated, and the concentration of phosphorus in that wastewater. To prevent phosphorus from reaching the lake, it is necessary to put the tile field far enough from the lake that the absorption capacity of the soil is not exceeded. Third is agricultural runoff. Because phosphorus is a plant nutrient, it is an important ingredient in fertilizers. Bound phosphorus is carried into streams and lakes through soil erosion. So that's all for the 7th subtopic. So for the 8th subtopic, it is about acidification of lake. So acidification of lakes. Most lakes are buffered by the carbonate buffer system. To the extent that the capacity of the lake is not exceeded, the pH of the lake will not be appreciably affected by acid rain. If there is a source of carbonate acid to replace that consumed by the acid rain, the buffering capacity can quite range. Carbonic acid releases bicarbonate into solution H1 from acid rain will also release bicarbonate. Thus, lakes forming calcareous acid tend to be resistant to acidification. Other factors that affect the susceptibility of a lake to acidification are the permeability and depth of the soil, the bedrock, the slope and size of the watershed, and the type of vegetation. The control of lake acidification is related to the control of atmospheric emissions of sulfur and nitrogen oxides. So that is all for acidification of lakes. Now for the last topic of water pollution. It is water pollution in estuaries. An estuary is formed along the coastline where fresh water from rivers and streams flows into the ocean. It is a place of transition where fresh water mixes with salt water. Estuaries are influenced by tides. Example, the Bay of Fundy, Boston Harbor, and Chesapeake Bay. The mix of saltwater and freshwater combined with a diurnal cycle of tidal wetting and drying and changes in salinity make the estuary ecosystem extremely complex. Numerous different habitats support an abundance of a wide variety of different animals. Each of these is sensitive to minor changes in the quality of the water. Like other surface waters, estuaries are subject to a plethora of pollutants. Although the technology and policies that serve to manage the water quality of lakes and rivers also apply to estuaries, the management of water quality is complicated by the number of political jurisdictions that touch on the estuary as well as the competing needs of organisms that live there. Competing with the environmental value is the economic value of the estuary to commerce. So, groundwater pollution. Groundwater, by its very location, has a large measure of protection from contaminants that are found in surface waters. However, once groundwater becomes contaminated, its location and low rate of replacement with fresh water makes it difficult to return it to a pristine state. Two major sources of contaminants are of concern: uncontrolled releases of biological and chemical contaminants, and saltwater intrusion from overpumping of wells. So first, controlled release. Uncontrolled release comes from a variety of sources. First, discharge of improperly operated or located septic systems, leaking underground storage tanks, improper disposal of hazardous or other chemical waste, spills from pipelines or transportation accidents, recharge groundwater with contaminated surface water, leaking landfills, leaking retention ponds or lagoons. The properties of the contaminant and the aquifer material govern their migration of the contaminants. Water-soluble chemicals are likely to move vertically down through the soil to the aquifer and migrate with the water. Example, nitrate, methyl tertiary butyl ketone, and methamidophos are examples of water-soluble chemicals. Second is saltwater intrusion. Freshwater aquifers near oceans or above saline aquifers may become contaminated with salt water when water is pumped from wells that draw water is too close to the freshwater saltwater interface. Because seawater is heavier than fresh water, it will form saltwater wedge in aquifers that drain into the ocean. Assuming that fresh water moves horizontally to the ocean and that the interface is abrupt and that it occurs at the shoreline, we can express the freshwater pressure at any point of the interface as freshwater pressure is equal to quantity height of water table above sea level plus distance of interface below sea level times the density of fresh water in kilogram per meter cube. This pressure must be the same as the saltwater pressure on the other side of the interface. That is, freshwater pressure is equal to Zp. Equating two expressions and solving for Z gives Z is equals to density of salt water over density of fresh water times height. So that is all for the water pollution in estuaries and for my report for water pollution. Thank you.